Good day guys, let's see another problem on moment of inertia. We'll go through it again, slowly but gently. Sketch the graph of x squared over 4 minus y squared equal to 1. That's the first important item I've picked up. And show the strip that you use to calculate the volume generated when the area in the first quadrant, this is very important, bounded by the graph, the y-axis, the x-axis, and the line y equal to 2 rotates about the y-axis. So from that story, that is what is important to me. So before I start doing anything, I have to capture all the important information. Then from there, we'll calculate the volume, moment of inertia, then express our answer in terms of the mass. So let's start taking out the important information. We've got x squared over 4 minus y squared over, or anyway, it's just y squared. If you choose to say over 1 is fine. It's equal to 1. That's the first information. Then they've spoken about the y-intercept, y-axis, y-axis. We must know that y-axis is a graph whose equation is x equal to 0. Then there is the x-axis, which is also a graph whose equation is y equal to 0. Then there is the line y equal to 2. Then what other thing? We're told about first axis, first quadrant. So we are interested in the area in the first quadrant. And finally, our rotation is y-axis rotation. So if I read that question, this is what is important to me. I take out all the important information. So looking at the number of graphs I have here, they are 1, 2, 3, 4. So each time I go through my equation and I see that I have 4 graphs, 2 of the graphs must be the limits of integration. And you read limits from the same axis. So it's obvious that our limits are from y equal to 0 to y equal to 2, because I must read everything from the same axis. So I will quickly indicate that these are my limits of integration. So another thing is you read limit where your strip touches. So this is already building an information in my brain that my strip must be touching the y-axis. Since the y-axis is vertical, the strip that touches the y-axis should be a horizontal strip. So even if I sketch the graph from this little information, I can already see that I need a horizontal strip since my limits are from the y-axis. So I guess we can now go and sketch our graphs. So our graphs will start with the x, the y, and the x-axis. Immediately we'll sketch that. We are done with 1, 2 out of 4 graphs. So that's what I'm doing. This is my x-axis and my y-axis. So I'm already done with 2 graphs. Then there is the graph y equal to 0, y equal to 2, sorry. So y equal to 2 should be a graph that touches the y-axis only. At 2, such a graph should be a horizontal line. So I will label it y equal to 2. Then I will put my number 2 there. Each time a graph touches an axis, we need to see a number. Then we can go to the difficult graph. This is our graph. So each time I see a graph with x squared and y squared, if the sign in between is negative, I know it's a hyperbola. If it was positive, I would be thinking about a circle or an ellipse, but with a negative, it's a hyperbola. And if you look at that hyperbola, you will see that if you were to make x 0, this negative will make it impossible to solve for y, telling you that hyperbolas do not touch the y-axis. But if I were to make y 0, you see, if we make y 0, we'll get x squared over 4 equal to 1. So x squared over 4, equal to 1 means if I multiply both sides by 4, I'll get x squared equal to 4, and therefore x is plus negative 2, telling me that that graph touches the x-axis at 2 and at negative 2. So the students who are familiar with the shape will know that this graph is supposed to be something like that on both sides. But we are not so interested on the left side because there was a special statement, first quadrant area. So even if we sketch the whole graph, where we have much interest is in the first quadrant. So in the first quadrant, we must shape the portions surrounded by 1, 2, 3, 3 and 4 graphs. So this is y equal to 2, you see it, the y-axis, the x-axis, and our graph. So the portion we are shading, which is of interest to us, is this portion. So that is the portion we are shading. So even if we didn't sketch that side, it's fine. Then it's important to put our 2 there, as we see down there. So that's our diagram. Now the next thing is to put our strip. If we have interpreted this information correctly, so you see that since your limits are coming from the y, your strip must touch the y-axis. Such a strip, it's only the horizontal strip. Another option is that a strip should forever touch only the same 2 graphs. So you see, if I put horizontal strip, whether I put it at the top, at the center, or at the bottom, I keep on touching the same 2 graphs. But if I go for vertical, you see there is a problem, because a graph will change on the way. That shows me that the vertical strip is not the best one here. So I'm now going for my strip. This is my horizontal strip. So my strip touches the y-axis, reminding me where I read my limit and how my formulas for volume and so on will end. Then another thing with horizontal strip is that once you've got a horizontal strip, then you must label your graphs using x. With x1 on the right side of the strip, x2 on the left side. So this side will be my x1, which is coming from the equation of the hyperbola. We have to go there and make x the subject. Then x2 is on the left side of the strip, which is the y-axis. Another name for the y-axis is x equal to 0. So what I'm left with now is to go through my hyperbola and make x the subject so as to see my x1. So the equation there is x squared over 4 minus y squared is equal to 1. If I'm making x the subject, y squared moves so that I get x squared over 4 is equal to y squared plus 1. Then the next thing is that my 4 will move, so I'll get x squared is equal to, multiply both sides by 4, I'll get 4 into y squared plus 1, so that my x is the square root of 4 into y squared plus 1. So that's what I call my x1. So my x1 is 4 into y squared plus 1. So there, I'm done with my graph. So it's now time to handle the B part, which is calculating the volume. So I've got all the information I needed in my graph. So I can go to the B part, which says calculate the volume described in the A part above. So if I want to calculate the volume, the first key information is my rotation. My rotation tells me how my formula for volume starts. So it tells me that my formula must start with a Vy. Then how does it end? I look at my diagram, I check the strip in my diagram. It touches the y-axis, so it ends with dy. So as an N6 student, I'll go to page 5 of my formula sheet, search for the formula that starts with Vy and ends with dy. So that formula is pi, the integral from a to b, x1 squared minus x2 squared dy. So if you have done your job the way I've done mine on your graph, you will see that x1 is on the graph, x2 is on the graph, everything you need, you see it on the graph. And that is the formula for the disk method. How do I know it? I see pi outside. The second way I know it is that my strip must be perpendicular to the axis of rotation. You see the axis of rotation is y, my strip is perpendicular. So that is how you can know that the formula is the disk. So you can now start substitution. A and B will read from the y-axis, that is if you didn't manage to interpret from there, you see it from 0 to 2, or if you go to the y-axis, you start from where you started shading on the y to where you ended, so that is your 0 to 2, then x1 square, you see that's your x1, if you square it, it simply takes out the square root. So if it takes out the square root, we'll be having 4 into y squared plus 1 dy. Why am I rushing to put dy? My x2 it's a 0, so I don't need it. Now I can start integration, but from my own way of doing integration, this y reminds me that anything that is not y can step out because that's a constant. So you can choose to leave it in, but I would prefer to take it out. We don't need that 4. will never integrate it, so that I'm simply integrating y squared plus 1. I don't need to be carrying the 4 into the same 4y squared plus 4. If you feel like doing that, it's not a crime, you can do that. But to make things easy, I keep it out. So I can now integrate. If I'm integrating y squared, it gives me y cubed over 3. I integrate 1, it gives me y from 0 to 2. Then I substitute my limit. My upper limit is a 2, so I get 2 cubed over 3 plus 2. Then my lower limit, it's a 0, so it's a 0 plus a 0. So it shows that the lower limit is gone. So what I'm left with is just to calculate the upper limit. So I can use my calculator to do that. So in my calculator, 2 cubed, you are 8. So I'm taking 8 on 3 plus 2 plus 2. That gives me 14 over 3. Then I multiply by the 4 outside. I get 56 over 3 pi. That's my volume. So my volume Vy is 56 pi over 3 unit cube. So you see, our volume should forever be positive. So that's how simple it is to get the volume. So let's now go to the C part, which says calculate the moment of inertia. So when I'm calculating moment of inertia, it's as simple as the way we did volume. The first thing is check your rotation. Our rotation was y-axis rotation. So I go to page 6 of my formula sheet. I start by copying the general formula for moment of inertia, which the only thing I add there is my rotation. So that formula is the integral from a to b, r squared to m, which continues at density, the integral from a to b, r squared dv. So that's my formula, my general formula for moment of inertia. Now the next thing is I have to develop this formula using my guide. So to develop it, all I need to do is, in the place of dv, I copy the formula for the volume. But one nice thing with N6 is that, with N6 method, is that if you discover that this volume is the disk method, then they've developed your formula for you already. You don't need to do it the way we do under shell method. All you need to do is go to page 6 of your formula sheet. You look under the topic called secular lamina. You will see a formula for I1. You copy it down because that's your formula that has been developed for you. So I will do just that. If I go to page 6, my IY is density pi over 2, the integral from a to b of x to the power 4. So what am I going to do? I will just try to incorporate the information on my graph. So I will simply be seeing that on my graph, my strip has x1 on the right, x2 on the left, even though x2 is a 0. So if I want to accommodate the information on my graph, instead of just writing x to the power 4, I will write x1 to the power 4 minus x2 to the power 4, which will still reduce to x to the power 4 dy because our x2 is 0. So that way we can now start substituting, but it's good to have that knowledge of writing it like this, because what if x2 is not 0? You cannot lose any information. So our a and b are the same a and b we used in the first part. So we'll now get our x1. Our x1 is the square root of 4 into y squared plus 1. That's our x1. Now we'll have to raise this to the power 4. So if we raise it to the power 4, our x2 is 0, making life easy for us. So you must remember that the power 4 is like the power 2 times 2. So if I'm raising something to the power 4, it's like I'm raising it to the power 2, then to the power 2 again. So if we raise it to the power 2, like we did here, the first thing it will create will be this one, 4 into y squared plus 1. So in that way, we will be getting pi density over 2, the integral from 0 to 2. We have our 4 into y squared plus 1. That is like we've raised to the power 2, then we will raise to the power 2 again. Because this 4 that you see there, the 4 you see there is the same thing as 2 times 2. So if I raise it to the power 2 first, it will take off the square square root to release 4 into y squared plus 1. Then I apply the next 2 to then go through. So if I apply the next 2, having 4 to the power 2, which is 16. 16 is a constant. I will take it out. So I'll get 16 density pi over 2. Then inside, I'll just be left with y squared plus 1, or this square dy. So that is what I'm left with, because I've squared 4, it gives me 16, then the square also comes in. So from here, I can then expand, and to do this expansion, I've explained this thing to my N6 students several times, that if you are expanding a plus b, all that square, I expect 3 terms. The first term you get a, you square 8. The last term you get b, you square 8. The middle you take 2 times a times b, you put in the middle. That's how fast you can expand if the power is 2. So apply that there, then where there is a, we will put in our y squared to get our 3 terms. So we'll continue this side. If that is done, our moment of inertia will become 16 over 2. It's a simple 8 density pi. The integral from 0 to 2. If I take y squared and square it, I will get y to the power 4. If I take 1 and square it, I will get 1. Then in the middle, I will take the power 2 times y squared times 1. That gives me 2y squared. Then I'll put my positive sign. There, I'm done with my expansion. I can now concentrate on integration. So I'll get 1 over 5 of y to the power 5 plus 2 over 3 of y to the power 3 plus y. That's my integration from 0 to 2. Then I put my limit. So I'll put 1 over 5 into 2 to the power 5 plus 2 over 3 into 2 cubed plus 2. That's my upper limit. Then I start the process all over again. Then I replace every y by 0. It means I'll get 0 plus 0 plus 0, since y is common everywhere. Then I go to my calculator and do the rest. So I will go through my calculator. 2 to the power 5, you add 32 over 5. So I get 32 and 5 for the first term. Then plus 2 to the power 3, it's 8. 8 times 2 is 16, so that gives me 16 on 3. Then plus 2. So that gives me 206 over 15. Then I multiply by 8 outside times 8. That gives me 1, 6, 4, 8. So I get 1, 6, 4, 8 over 15 pi density. So that is my moment of inertia. If I'm interested in unit, I can just put u to the power 5. Coming from there, volume was u cubed, and that is u squared. So that's how easy it is, guys, to get your moment of inertia. Then we can go to the last part, which says we should express our answer in terms of the mass. So if you look at the last part of moment of inertia, it says express your answer in C above in terms of the mass. So again, in this part, the little thing I want to explain to you is that you must go to page 5 of your formula sheet, look for the relationship between density, volume, and mass. Then from there, if you make density the subject, you see that density is mass over volume. So with that relationship, it shows that here, I can replace that by mass over volume. So the easy thing I do is that to get my answer in terms of the mass, I will take my moment of inertia, I divide by my volume. Since this is telling me so, then I multiply by m. So that's what I will do. My moment of inertia is 1648 pi over 15. You see, I'm not using density. I will simply know that density is replaced by this. And to do that, I simply divide this answer by my volume. My volume was 56 pi over 3. So I get 56 pi over 3. Then whatever I get, I multiply by m. So in my calculator, I know that pi divided by pi will cancel. So I will simply be taking 1648 over 15 divided by 56 on 3. So if I do that, it gives me 206 6.35 m. If you want your answer in decimals, it's still not a problem. You can get 5,886 m. So guys, this is our moment of inertia in terms of the mass. So thank you very much. I hope that will help us